All right. Last but not least, 12 through however many. 20. Yeah, it's not bad. Most of them are not too long. Okay. Cool. Students in an online course are each randomly assigned to receive either standard practice exercises or adaptive practice exercises. For the adaptive practice exercises, the next question asked is determined by whether the student got the previous question correct. The teacher of the course wants to determine whether there is a difference, and underline that, between the two practice exercise types by comparing the proportion of students who pass the course from each group. The teacher plans to test the null hypothesis that P sub S equals P sub A versus the alternative hypothesis, P sub S does not equal P sub A, where P sub S represents the proportion of students who would pass the course using standard practice exercises, and P sub A represents the proportion of students who would pass the course using adaptive practice exercises. Setting the hypothesis, defining just in a big chunk of text. The teacher knows that the 99% confidence interval for the difference in proportion of students passing the course for the two practice exercise types, standard minus adaptive, is 0.03 to 0.24. And the 90% confidence interval for the difference in proportion of students passing the course for the two practice exercise types, same thing, standard minus adaptive, is 0.06 to 0.21. What is a reasonable conclusion for the teacher's hypothesis test at the sigma alpha equals 0.05 significance level? Okay. A reasonable conclusion is so it is reasonable to conclude there is a significant difference at the 0.05 significance level because the 99% interval for the difference did not include 0. So this implies a significant result at the 0.01 level. So basically, if it's significant at the 0.1 level, 0.01 level, excuse me, it's going to be significant at any of the levels that we typically use. Because if it passes this bar, it's going to pass this bar. And that's basically it. So the confidence interval for differences, not including 0, means that we have a significant result at 1 minus the confidence percent significance level. Cool. 13. PHS surveyed 500 students and recorded their gender and whether they attended at least 2 school events. Of the 210 female students surveyed, 147 said they had attended at least 2 school events. So that's 147 out of 210. If gender and school event attendance are independent, how many male students would we expect to say they had attended at least 2 school events? You can do this a few different ways. Because they're independent, we're expecting this same proportion to hold for the male students as well. When you pop that in your calculator, you're going to get that this is 70%. So there are 500 minus 210 male students, because 210 are female, which means there's 290 male students surveyed. And then if we take 70% of 290 male students, we get 203 we would expect to say they had attended at least 2 school events. The other way you could do this is 147 over 210 equals x over 290, cross multiply and divide, right? Solve for x. You could also do this with the 500 students, figure out how many total students would say they had attended 2 events, and then subtract the girls out. Lots of different ways to go about this. All are acceptable. The key is if they're independent, this proportion is going to be the same regardless of gender. Okay. Allie is measuring the animals in the museum and records her measurements in inches, but the museum wants to present a paper at a European conference and needs to convert the measurements to centimeters. What is the correlation between measurements in inches and the measurements in centimeters, and why? Okay, so the correlation will be 1 because there's a constant relationship between inches and centimeters. So it's going to create a perfectly linear relationship, and therefore the correlation will be 1. So 1 and -1 are perfectly linear. Converting it to centimeters, the values in centimeters are going to be higher, so that's why it's +1. If it were centimeters to inches, we'd be multiplying by the same value less than 1, and so it would be a -1 correlation because they'd be consistently, in the exact same way, proportionally lower. Okay. Researchers will conduct a study of the television viewing habits of children. They will select a simple random sample of children and record the number of hours of television the children watch per week. The researchers will report the sample mean as a point estimate for the population mean. All this means is, point estimate is we're using our sample mean because we think it's reasonable to estimate that for the population mean. If we did this over and over and over again with the same samples of the same size, we'd get a normal distribution around the population mean because point estimate, the mean should be an unbiased estimator. Okay. Which of the following statements is correct for the sample mean as a point estimator? Okay, sample size of 25 will produce more variability of the estimator than a sample size of 50. Okay, as sample size goes up, variability goes down. If you're feeling like you need to stretch, always good to think about sample size and variability. Right, so there's an inverse relationship between sample size and variability. So this is looking pretty good. Sample size of 25 will produce less variability than a sample size of 50. No, that's the opposite. That's not true. The rest of these are about the amount of bias. That is not going to be really affected by the sample size. The point estimator is biased or unbiased based on whether or not it approximates the actual population parameter. And it's going to do that, over time, regardless of sample size. I mean, the sample sizes we're not going to get into that too much. Okay. Sample size goes up, variability goes down. If you can remember that, you're like 2/3 of the way there. Cool. This was on your final. A roadrunner is a desert bird that tends to run instead of fly. While running, the roadrunner uses its tail as a balance. A sample of 10 roadrunners was taken, and the bird's total length in centimeters and tail length in centimeters were recorded. The output shown in the table is from a least squares regression to predict tail length given total length. We're using this. Here's our slope, or our y-intercept, excuse me. And here's our slope. Do what I write, not what I say. Okay. Suppose the roadrunner has a total length of 59 centimeters and a tail length of 31.1 centimeters. Based on the residual, which is actual minus predicted, does the regression model overestimate or underestimate the tail length of the Roadrunner? Okay, let's set up our equation first. Predicted tail length is negative 1.281, that's our y-intercept, plus, because it's a positive slope, 0.5264 times our total length. You should define total length as x and predicted tail length as y hat. Okay. So we're going to plug our 59 in for our total length. We get negative 1.281 plus 0.5264 times 59. Let's see what that is. Negative 1.281 plus 0.5264 times 59. And we get that the predicted tail length is 29.7766 based on the residual. So the actual tail length was 31.1. So actual minus predicted. 1.1 minus that is 1.3234. So the regression model here is an underestimate because the residual is positive. The predicted length ended up below the actual length, so it was an underestimate for that bird. Beep, beep. Okay. 17, getting there. Teacher believes that there is a linear relationship between the amount of absences a student has and their grade in the class. That is, fewer absences should mean higher grades, and more absences should mean lower grades. The teacher collects a lot of data on students' absences and grades and fits a linear model. If a linear model is appropriate, what should be apparent in the residual plot? Drum roll. Nothing should be apparent. There should be no apparent patterns in the residuals if the model is appropriate. You are going to keep seeing these on your tests until nobody misses it. See. All right. 18. Distribution of the length of employment for workers at a factory is moderately skewed to the right, with a mean of 7.4 years and a standard deviation of 5.6 years. We're describing the sampling distributions for a sample of size 15 and of size 150. 15 is less than 30. 150 is more than 30. I'm just making a note of that. So the mean is still going to be 7.4 years. The mean is going to be the mean is going to be the mean. The standard deviation is going to be the standard deviation over the square root of the sample size. And the shape, because we are dealing with a sample size of less than 30, and the population is not normal. The population is skewed and our sample size is less than 30. We're going to be moderately skewed right. It's going to retain its shape if the sample size is less than 30. Alternatively, for this set, the mean is also going to be 7.4. The mean is just the mean. The standard deviation is always going to be the standard deviation for 1 over the square root of the sample size. So as this goes up, this is going to get smaller, right? As sample size goes up, variability goes down. Standard deviation is a measure of variability. Essentially, we're dividing the same number by a larger number. That's what's going on. And then because our sample size is greater than 30, the shape is now going to be approximately normal. So all that freaking out and teeth gnashing for unit 5, this is it in a nutshell. And 15 is less than 30, which is why the shape is this way. 150 is greater than 30, which is why it ends up approximately normal. Cool. 2 more. All right. Following list shows the number of video games sold at a game store for each day. Attacked by sneezes. Sold at a game store for each day for 1 week. Here they are. Which of the following is the best classification of the data in the list? So this is a number, excuse me. This is a number of video games, and these numbers have numerical meaning. The fact that 20 were sold this day means that's more than the 16 sold on this day. So these are quantitative variables. We're going to get rid of anything that says categorical, and then it is quantitative, so it's not nor quantitative, right? We can knock that one out. Just as a side note, and I put this in the written key already, don't pick answers like E unless you know exactly why the other 4 are definitely wrong. If you were just blind guessing on this, guess one of these other 4. Cool. Now, difference between continuous and discrete is just, would it make sense for any of these numbers to be something other than whole numbers? Can we have the in-betweens? And since we're talking about video games, well, we've either sold 15 or we've sold 16. We're not going to sell 15 and a half video games without getting fired. So it's not continuous, which leaves us with quantitative and discrete. Okay. Last but not least, expected value. I know, I'm reading ahead. Yada, yada, bulk, wholesale prices, retail prices. Here's the estimates for next year's sales. What profit do we expect if each calculator is $20 at wholesale and $30 at retail? We're going to do this in one big equation. You could put this in your lists as L1 and L2, and then that's going to give you, when you do the one variable stats with L2 as your frequency, it's going to give you the number. Then you would just multiply that by the cost, respectively. Just going to write it out. It's just as easy. So we have $20 times 2,000 with the 0.1, 5,000 contributing at 0.3, 10,000 contributing at 0.4, and 20,000 contributing at 0.2. Plus $30 times 600 at 0.4, 1,000 at 0.5, and 1,500 at 0.1. When you do that, be careful when you're typing it in, but you can type this in all at once. 2,000 times 0.1. I'm going to see if I can find it from when I did this earlier. It was like 220,000 something. I did this both with the list and by typing it out. And yeah, it's $220,700. Not bad for a year's profit. We did it. Okay, now, because you've made it this far, we've gone on this journey together, I'm going to introduce you to my cats. They're asleep, so they're going to be mad. All right, so this is the first. All righty. Here we go. So this is Baby. She was just taking a nap. She's not very happy about being woken up.
but she is a very sweet, nice baby. Say hi, baby. Oh, she's so mad. I'm gonna go put her back.
And then number 2, he's gonna run.
This is Buddy. He's very handsome. And he's a scaredy cat. And now they get chicken treats.